So in this video, we're going to cover a couple new reactions. So Friedel-Crafts alkylation and acylation, and we're going to look at some different substituent on benzene rings to see how that changes these electrophilic aromatic substitution reactions. So this reaction, just like all the other ones we've seen, has benzene here, right, acting as our nucleophile. We have our Lewis acid here at the bottom, and then we have our source of an electrophile group. So in this case, we'll have an electrophilic carbon. And you can see here we're adding a carbon to benzene, right? So we're making a new carbon-carbon bond by adding an alkyl group. So the CH3Cl could be any, it could be an ethyl group, a propyl group, whatever. It would still add onto the benzene ring in full. So the mechanism for this, kind of like many others we've already seen, has the chlorine on this chloromethane here, coordinating again to the Lewis acid, kind of making the carbon more partially positive and the chlorine more partially negative. And so our benzene, our nucleophile here, will come in and attack our electrophile, generating our reactive carbon intermediate here, again, which is also, right, resonance stabilized from those nearby double bonds, right, that positive charge can delocalize. And the final part, we have a base, Cl- in this case, right, coming in to generate our products here, right, specifically our alkylated benzene. However, there's some issues with this reaction that we should be aware of for why it doesn't work super great, and we'll see a way to kind of do this a little differently. There's a few different side reactions that can happen here. One is called polyalkylation, which just means, right, poly means many, right, so the name here means many alkylations are happening. Essentially, the product for this reaction is more reactive than the starting material, right? So for example, in the last reaction we had, right, with benzene, we're adding on some sort of alkyl group. I'll make it different just because, right, we have ethyl chlorine. And so there are, intended product for this reaction, right, is one ethyl group being added here. However, we actually get a mixture of products where we actually have multiple alkyl groups adding here at the end. So essentially we get to this, and then that reacts even further with our conditions here. Okay? These alkyl groups in general, right, if you remember from our talks of stabilizing carbocations, alkyl groups are electron donating, right, because carbons are partially negative in comparison to hydrogens. And this makes the benzene more nucleophilic. Right, we're lowering the transition state, number one, right, going from benzene to that intermediate. Another problem is we can get rearrangement occurring. So we have very similar, but instead of having ethyl or methyl, let's look at propyl chlorine. And in this case, our minor product actually is propyl chlorine, but our major products are this rearranged propyl group, isopropyl, plus all these polyalkylated products too, right? So we get all of what we have up above in number one happening as well. So the mechanism for this, I'm going to kind of shorthand it here, is, right, we have our chlorine here, right, coordinating with our aluminum, and it'll actually fall off, essentially, to get to this carbocation intermediate, right, our electrophile, and we get a hydrogen shift occurring, right, because we want to get to the more stable carbocation intermediate. And so we actually get this as our more stable, right, carbocation intermediate. So we have a new electrophile here. Okay, so these are all the reasons why this reaction doesn't work super well. So the way we can kind of modify this is to do the following. Where instead of having a alkylation, we have an acylation, right? An acyl, we talked about this in an earlier chapter, but it means this carbonyl-based group here. So we're adding on an acyl group to our reaction. And we do this with something called an acid chloride. And here, no rearrangement or polyalkylation occurs. And for the mechanism, I'll leave this up to you, but it's essentially going to be the same thing. We're getting chlorine, right, coordinating to the aluminum, and then we're generating the rest of the acyl group as our electrophile, right? We have a acyl electrophile. Okay, so now that we've looked at a bunch of these reactions here, let's go ahead and look at what happens when we add substituents. And so we're going to look at some different effects here of different substituents on our benzene ring, okay? And so if we're looking at toluene here, right, just methylated benzene, what happens when we do this nitrate reaction, right? We're adding on this NO2 as our electrophile, okay? We can get potentially, right, because that methyl group here has taken up that carbon, so we can't actually add the nitro there. So instead, we get the following products with a nitro group here, a nitro group here, and here, all the way at the bottom. Right, so we have ortho, meta, and para, right? Remembering our terminology here, the nitro group is ortho to the methyl group here, it's meta to the methyl group here, and it's para here. And so what's happening, right? Which one forms in majority? And so what we see here is that actually we get the ortho and para groups as the major products. About 60% ortho, 40% para, and about 0% meta. We get a little bit, but it's effectively 0. Okay, and this is because the methyl group here is an electron donating group. And we'll see why that matters in a little bit. But because we could do these electron donating groups, or if we have electron withdrawing groups, it changes the reaction, right? So these electrophilic aromatic substitution reactions, the EAS reactions, allow for selective additions of groups. And for electron withdrawing groups like this trifluorocarbon here, right, these fluorines are pulling electron density away from the carbon, making this carbon, right, partially positive, right? If you can see that little scribble I drew there, it's partially positive. So in this case, the major product is actually the meta group, the meta position. So this forms about 90% for the meta, and for the ortho and para, we have about 10%. Okay, so when the hold on, sorry, I did that backwards, right? It is the same molecule, but I just drew it backwards. When that nitro group gets added to the benzene, we see that in the meta position, it's 90%, and when the nitro group is added, ortho or para, it's about 10%. Okay, because it's electron withdrawing. And so, why is that? We'll get to that in a second. But like we mentioned, the Friel-Crafts part, right? These electron donating groups are more reactive, okay? And the reason why we get a difference in products here, right, with ortho-para being major for donating groups and meta being major for withdrawing groups, depends on the stability of the intermediate. right, that rhenium ion intermediate, right, that positively charged intermediate, like I mentioned in class, is really important to our reaction here, right? So we have our intermediate, He, and then we have a substituent somewhere on the molecule, which we can denote as X, right? And so our starting material, right, again, benzene with some substituent somewhere, we're just denoting as X. What we end up seeing is, right, for the intermediate, the energy levels is higher, right? But depending on where it is, depends on the substituent we're adding, right? So when ortho-para, when we have a withdrawing group, it's going to be higher in energy than if we have meta group. If we have regular old no substituent, it's kind of in the middle here. And when we have electron donating group, it's lower in energy. Okay, so we can kind of draw the transition state energy pathways like this. We can see we get lower in energy as we're adding on electron donating groups, right? So the products are dependent on the stabilization of the, right, on that intermediate, on the carbocation intermediate. Right, and the lower energy, right, lower energy means faster reaction. Okay, I know there's kind of a lot of information. We'll go over it in class too, but I want to sort of highlight on why this is happening, right? Why this intermediate is making these reactions go either fast or slow, and why they're directing the way they are. Okay, so let's go ahead and take a look at this first example here with our electron donating group. Okay, so we can see here, right, electron donating. Right, we're still doing these nitration reactions. And so we're going to look at the intermediates here for each of these, okay? So we have the nitric group added. Again, we have all these intermediates on the left, right? And the nitric group has added ortho in the first example. It's added meta in the second example, and we're adding it para in our last example here, okay? And we can look at the resonance structures for these to get a feeling for why, right? Remember in the last example here, we said electron donating groups, we get the ortho-para as the major product, right? Adding the nitro group ortho-para as the major products. Okay, and so why is that? So we have to look at the resonance structure. So for our first example here, where we've added on our nitro groups here, right, we can make resonance structures by pushing those electrons around the ring here. And we can kind of keep going, right? And so when we get to this resonance structure here, yes, right, resonance structures are great for pushing around positive charges, but what we can see now is the positive charges ended up on the carbon where we have our electron donating group, right? That carbon is slightly partially negative, and that is next to our positive charge, right? Do we see that? Because these alkyl groups, right, are electron donating, it is stabilizing the positive charge, right? That partially negative carbon is sort of adding its electron density to the positive charge, bringing the transition state energy down, right? We're lowering the transition state energy, we're lowering the energy, we're getting a faster reaction, okay? For 2, I'll leave the doing resonance structures up to you, but this has no resonance structure with positive charge on the CH3, right? So this is not stabilized, right? Not like the ortho or pair directors are. Because for the pair director, we can do the same thing. We can push electrons down here. We see the CH3 with a positive charge here. And again, we get the stabilization effect, right? Our electron donating group is right next to that positive charge. So this is why, right, the ortho, we get ortho-para as major products for electron donating groups. So now what about electron withdrawing groups? Right, we said those are directing meta. So let's take a look at some of those. So like in that last example we just showed, we have the CF3 here, right, which we know is electron withdrawing, because these fluorines, these halogens, are pulling away electron density, right? So this carbon is pretty electron positive, right? So this is a electron withdrawing group. And so once again we have our intermediates, right, on the left for this reaction, this nitration reaction, where we have ortho, meta, and para substitution examples, okay? And so if we are looking at ortho here, same as before, I'm going to kind of jump here to go all the way to the resonance structure we want. So we're doing 2 areas instead of just the one. And when we do that, we can see a resonance structure we get has the positive charge, again, like we saw before with the alkyl group, on that carbon here. Right, and this isn't great. Right, this is actually destabilized from our carbocation being near the electron withdrawing group. Right, so that positive charge here is essentially even greater of a positive charge, right? It's getting pulled even further by the CF3, right? Making it very not stable, right? So this is a really bad resonance structure, making it not want to go through that ortho or para position. Right, that carbocation is on the CF3, right? But the meta position, and leave the resonance structures up to you, there's no positive charge, no carbocation on CF3, making the meta position the most stable product. Right, so in this reaction here, right, if you draw the product for the reaction, it would look like this. Right, CF3 with our major product being NO2 here, right, this meta product, while ortho and para, essentially, there's little to no reaction, right, it's about 10%. So our major product here is the meta product, right, meta is major product, right, because this is the most stable intermediate pathway without that destabilization effect that the ortho and pair positions see. So what other groups can be ortho or electron donating, electron withdrawing groups? So here's a general list of them, okay? So we have these groups here that we call ortho-pair directors. And these are those electron donating groups, right? We call them ortho-pair directors because they direct groups going to the ortho and pair position, like we just discussed, okay? And we have some that are strong activators, right? So this makes the reaction faster, right? So groups like OHs, nitrogens, these make the reaction go faster, right? They have lone pairs that are ready to donate, right? And weak activators are things like these alkyl groups, where they don't make resonance structures, but, right, these carbons, right, carbons are partially negative, slightly, so they donate weakly. So it makes the reaction faster, but not as fast as the strong activators. And right in the middle here, we have the halogens. And so the halogens are ortho pair directors, but they're really slow, they're really weak. And that's because halogens have lone pairs to donate, but they're really electronegative. So they're slower, right? So while they still direct ortho and para, they're slower. They're deactivators, okay? And so our last list here are the meta-directors. So these are the electron withdrawing groups. Right, and so here we have the groups that have no lone pairs attached on the atom connected to benzene, and they're partially positive, right? Just like we saw with CF3 here, right? All of these groups here, right? Carbon, nitro groups when they're the already existing substituent, right? Groups with positive charges. These are all things that are pulling away electron density, right? Making that intermediate not very stable, okay? So we have some examples here of strong and weak meta-directors. All right, and they're also deactivators because the reaction goes kind of slow, right? They're not really the most stable intermediates in the world. So I know this was, again, a lot of information, right? We learned a lot of kind of different things here, but it's all connected to the intermediate, right? That rhenium ion intermediate for all of these benzene-based reactions. And so in class, we'll do a lot of these examples, right? We'll go through, particularly starting with, on the next page here, we're going to look at some examples of these two reactions and adding on groups to them and seeing where the groups go and why they go there. So we'll be spending time in class looking at the mechanism and resonance of these benzene reactions and these rhenium ion intermediates.